We see AI do all these incredible things, but have you ever stopped to wonder how it actually learns? It's not some clean, perfect process. Oh no. It's a journey, and it's full of challenges, dead ends, and some really brilliant breakthroughs. So today, we're going to go under the hood and follow the real, kind of messy path an AI takes to learn what seems like a pretty simple task.
All right, let's get into it. Here's the plan for our journey today. We're going to start with a classic challenge. Then we'll have to face the huge difference between learning and just memorizing stuff. We'll see what success actually looks like. And then, this is the good part, we're going to tackle two of the biggest roadblocks in deep learning history before we finally put together our modern AI toolkit. So, what's our quest? It's to teach a machine to do something that you and I do without a second thought: read someone's handwriting. We're going to train a neural network to recognize a single handwritten digit. Sounds easy, right? Well, this one little task is going to show us all the core challenges of machine learning. And this right here is our textbook. It's called the MNIST dataset. It's a massive collection of 60,000 handwritten numbers, all drawn by real high school students and Census Bureau employees. And just look at the variety. Some are neat, some are super sloppy, others are slanted. Our network has to figure out the essential sevenness of a 7, no matter how it was drawn. This is its training ground. Now here's the absolute key. We could, in theory, just have the AI memorize every single one of these 60,000 images, like a giant digital flashcard deck. But that's not learning, is it? The real test, the true measure of intelligence here, is what we call generalization. Can our network look at a handwritten 5 that it has never seen before and still know it's a 5? That's the entire game. So that brings us right to our first major hurdle on this journey. It's a classic trap that pretty much every learning machine falls into at the beginning, and it's called overfitting. Overfitting is, well, it's exactly what it sounds like. The model gets so obsessed with the training data, it starts learning all the noise, the little quirks, the specific way one person happens to write a 4. It's like a student who crams for a test by memorizing the answers from a study guide, word for word. They'll ace that specific test, no problem, but give them a question that's even slightly different, and they are completely lost because they never actually understood the concepts. Okay, this graph is basically an EKG for a learning network, and right now it's showing a big problem. That red line, that's the error on the training data, the stuff it's studying. And look, it's going down, down, down. Perfect. But look at the blue line. That's the error on brand new images it has never seen before. It goes down for a little while, but then it starts to creep back up. That split, where the lines start going in different directions, that is the classic textbook sign of overfitting. Our network isn't learning anymore. It's just memorizing. So if that last graph was our patient getting sick, what does a healthy, well-trained network look like? What are we actually trying to achieve here? Now this is what you want to see. This is a healthy learning process. Notice how both lines, the red training error and the blue test error, are moving down in harmony. They eventually flatten out, the gap between them is nice and small, and they stay stable. This is the graph that tells us our network is actually learning to generalize, not just getting an A+ on its homework. Okay, so let's say we've dodged overfitting and our network is learning really well. But as networks get deeper, with more and more layers, a much weirder, more subtle problem can pop up. Sometimes, for what seems like no reason at all, the learning just stops. The network just freezes in place, completely refusing to get any better. This is called the vanishing gradient problem. To get this, we have to look right at the heart of a single artificial neuron, at its activation function. This thing basically decides how strongly the neuron should fire based on the signals it gets. Think of it like a dimmer switch for a light. On this graph, the horizontal axis is the input signal coming in, and the vertical axis is the neuron's output. See that nice steep curve in the middle? That's the sweet spot, the learning zone. A small change in the input signal causes a big change in the output. But now look at the ends. See how the lines go totally flat? In these saturated regions, you can crank the input up or down a ton and the output barely moves. The dimmer switch is either all the way off or all the way on. The neuron has effectively stopped listening. And that creates a massive problem. See, learning happens when the network sends an error signal backward from the output, telling each neuron how to adjust itself. But if a neuron is stuck in one of those flat, saturated regions, it basically says, hey, I'm not the problem, and passes back an almost zero signal. As this tiny, tiny signal gets passed back through layer after layer of saturated neurons, it shrinks and shrinks until it basically vanishes completely.
By the time it reaches the early layers of the network, there's no signal left. They get zero feedback, and so learning grinds to a complete halt.
So the goal then is to figure out how to keep our neurons out of those flat, dead zones. And engineers came up with a whole toolkit to do just that. There are smarter ways to set up the initial random weights in the network, so neurons don't start out already stuck. There are ways to standardize the input data, scaling it so it falls right in that active range. And there's a really clever technique called batch normalization, which actually recenters the signals inside the network while it's learning. It's all about keeping those neurons in that responsive learning sweet spot.
But there's another way to fix a stalled network, and it's even more powerful. It's not about nudging the neurons around. It's about completely changing how the network even thinks about its own mistakes, redefining how it measures error in the first place. So the really big question became, what if the way we're measuring error is actually part of the problem? Is it possible to design a new formula for error, a new loss function that sends a louder learning signal exactly when the network is the most confident and the most wrong? This slide shows a really tragic flaw in a common error function called mean-squared error, or MSE. So look over on the far right. The network is totally confidently wrong. It's outputting a 1 when the right answer is 0. But now look at the green line, which is the actual learning signal it gets. It's flat. It's at 0. The network is screaming the wrong answer at the top of its lungs, and our error function is telling it, nope, you're good, no need to change. Learning has completely stopped. So the solution was to give our network a new teacher, a totally different way of measuring error called cross-entropy loss. This function is designed specifically for classification tasks like ours. And its magic is that it doesn't just care that the network is wrong, it cares about how confidently it's wrong. And it dishes out a much, much bigger penalty for those super confident mistakes. And this graph shows you the power of that new teacher. Look at the right side again, where the network is most wrong. See what's happening? The blue line, our cross-entropy loss, just skyrockets. And because of that, the green learning signal is now the strongest it can possibly be, right where we need it most. Now, when the network screams the wrong answer, cross-entropy gives it the biggest possible kick in the pants, forcing it to learn. Putting these two side by side tells the entire story. On the left, with mean-squared error, the learning signal just dies when the network gets stuck. It gives up. But on the right, with cross-entropy, the signal absolutely roars to life. It provides this powerful corrective force that basically breaks the network out of its funk and guarantees that learning can always keep going, especially from its biggest blunders. This was a revolutionary change. Okay, so let's take a step back and see how all of these pieces, all these hard-won solutions to tough problems, come together to form the very foundation of modern deep learning. So there we have it. We've walked the path. We started with a clear goal. We learned to be on the lookout for that overfitting trap, always making sure our network is actually generalizing. We built up a whole toolkit of clever tricks to stop the vanishing gradient problem and keep our neurons listening. And finally, we gave our network a much smarter teacher, a loss function like cross-entropy, to make sure it learns super fast from its worst mistakes. The big takeaway here is that deep learning isn't just about making networks bigger and bigger. The real breakthroughs, the things that made today's AI possible, came from solving these fundamental nitty-gritty problems. Overcoming these challenges like vanishing gradients and figuring out the right way to even measure a mistake, that's what separated a simple little network from a truly powerful deep learning system. And that leaves us with one last thing to think about. We've just walked through the solutions to some of the biggest roadblocks in AI history, but this journey is far, far from over. So the real question is, what are the vanishing gradient or overfitting problems of today? What are those subtle, hidden challenges that researchers right now are banging their heads against the wall trying to solve to unlock the next generation of AI?